You are sitting on a rock, hurtling through space at a speed of 670,000 miles per hour. This rock orbits around a nuclear furnace that is 1 million times larger than itself. That furnace is just one of 400 billion stars orbiting within a vast galaxy that light requires a full 100,000 years to cross. But now, I will tell you something that will challenge your mind. Our entire galaxy, with its billions of worlds and countless civilizations that could exist, is nothing more than a single grain of sand in an infinite ocean containing 2 trillion others.
Imagine yourself in the very center of New York City at midnight. Lights stretch endlessly in every direction. Buildings blend into the darkness on the horizon. Now imagine that this cityscape spreads not just to the next state, but across the entire continental lands of the United States. Then extend it across the Pacific Ocean all the way to Asia. Continue extending it around the entire Earth. Then multiply this distance by 6 billion. This is a visualization of the width of our galaxy.
Scientists confirmed through precise measurements that the Milky Way's width from one end to the other is 100,000 light-years. 1 light-year is equal to 6 trillion miles. This means that our galactic home is 600,000 trillion miles wide. But this is the part that astonishes human intuition. Despite this mind-blowing scale, our galaxy represents only the first step on a cosmic ladder climbing into infinities that our brains cannot process. Every point of light sparkling in the night sky belongs to our galactic neighborhood. The hazy band of stars cutting across the dark sky reveals a sideways view of our spiral arms. From our position, approximately 26,000 light-years from the galactic center, we can observe star formation regions where new suns are ignited. Each year, we witness stellar nurseries where gravity transforms gas clouds into burning spheres. Old red giants end in magnificent explosions that fill space with heavy elements. All of this cosmic drama unfolds in our local galactic theater. Yet what truly makes this scale disturbing is not its size, but what it represents. Our galaxy forms a single unit within a hierarchy of structures that become increasingly vast and incomprehensible. Each level of cosmic organization dwarfs the previous one by factors that render human experience meaningless. Standing on Earth and thinking about galactic distances is like an ant trying to comprehend the size of North America.
Our evolved brains, designed for hunting on African plains, struggle with scales beyond our immediate surroundings. This cognitive barrier becomes our first clue that the universe operates at levels far beyond human intuition. Every cosmic structure we discover forces us to abandon earthbound perspectives and embrace scales that feel more like mathematical abstractions than physical reality. Light moves faster than anything else in the universe. Nothing can overtake a photon racing through the vacuum of space. At a speed of 670 million miles per hour, light circles Earth 7 times in a single second. This cosmic speed limit represents the fastest possible way to traverse distances in our reality. Yet even light, the ultimate speed champion of physics, requires 100,000 years to travel from one end of our galaxy to the other. Consider what this means for the human perspective. The light leaving distant stars in our galaxy tonight began its journey when early humans first learned to make fire. The photons reaching Earth right now departed from the far side of the Milky Way before written language existed. These ancient particles of light carry information about stellar events that occurred while our ancestors were still discovering agriculture.
Scientists use this light travel time as a cosmic measuring stick.
When astronomers observe distant galactic regions, they see them as they existed thousands of years ago. The galaxy we observe tonight is actually a mosaic of different time periods. Nearby stars show us recent events. Distant stellar neighborhoods reveal ancient history. We never see our galaxy as it exists right now. Instead, we see it as a time-averaged composite spanning thousands of years. Light from various galactic regions departed from its sources at different historical moments. Looking at the Milky Way means looking backward in time over a period longer than human civilization. But this process becomes even more mind-bending when we consider galactic rotation. Our entire galaxy rotates like a cosmic merry-go-round. The solar system orbits the galactic center once every 200 million years. Even more disturbing is what this implies about cosmic communication. Attempts to send signals across our galaxy face this fundamental barrier. Radio waves and laser beams travel at the speed of light. This means that galactic communication requires patience measured in geological time. If an alien civilization on the far side of our galaxy sent us a message today, our great-grandchildren's great-grandchildren would have to wait to receive it.
Step outside on a clear night and find the brightest star in the sky. This bright point of light is Sirius, and it shines 25 times brighter than our sun. It appears so bright that ancient civilizations based their calendars on its movements. To your eyes, Sirius looks close enough to reach with a long ladder. Confirmed reality completely shatters this illusion. Sirius is 8.6 light-years away from Earth. This distance is equal to 51 trillion miles. If you could travel toward this nearest bright star in a car at highway speeds, the journey would take 300 million years.
However, Sirius is almost next door compared to typical galactic distances. Most stars in our galaxy are separated by vast gaps that defy human comprehension. The average distance between neighboring stars measures 4 light-years. In cosmic terms, this represents an almost perfect vacuum, occasionally interrupted by small islands of matter. To visualize this emptiness, imagine shrinking our solar system until the sun becomes the size of a basketball. At this scale, Earth would be a grain of sand orbiting 26 feet away. The nearest star would be another basketball, perhaps located in Denver if you started from New York. Everything between these basketballs contains essentially nothing but empty space. This emptiness creates profound implications for interstellar space travel. The space between stars also explains why alien contact is so unlikely, despite the immense number of potential worlds. If alien civilizations exist on planets orbiting distant stars, they also face the same fundamental space and time barriers that isolate us. The universe conspires to keep intelligent species separated by vast chasms, too wide for meaningful interaction.
The space between stars also explains why alien contact is so unlikely, despite the immense number of potential worlds. If alien civilizations exist on planets orbiting distant stars, they also face the same fundamental space and time barriers that isolate us. The universe conspires to keep intelligent species separated by vast chasms, too wide for meaningful interaction. Scientists have calculated that our galaxy contains roughly 400 billion stars. Yet these countless suns are spread so sparsely across galactic space that each exists in magnificent isolation. Imagine counting every star in our galaxy. Begin with the sun and work outward along the spiral arms. Maintain a steady pace of 1 star per second without stopping to sleep or eat. After 12,600 years, you would finish counting.
Observations confirmed by space telescopes reveal that our galaxy contains between 100 billion and 400 billion stars. The exact number remains uncertain because dust clouds block our view of distant galactic regions. However, even the conservative estimate of 100 billion stars overwhelms human comprehension. Each of these stellar furnaces burns with the power of nuclear fusion. Every second, our sun converts 4 million tons of matter into pure energy.
The Milky Way's total energy output exceeds humanity's power consumption by factors that require scientific notation to express. Astronomers classify the Milky Way as a medium-sized spiral galaxy. Larger galaxies contain more than 1 trillion stars. Smaller dwarf galaxies host only a few billion stellar furnaces. The probability mathematics surrounding galactic star counts suggests mind-bending possibilities for planetary systems. Even if only 1% of galactic stars host Earth-like worlds, our galaxy contains billions of potentially habitable planets. Some of these worlds may harbor civilizations far older and more advanced than human society. Others may contain life forms so alien that we lack the vocabulary to describe them. However, what truly makes these numbers disturbing is their cosmic insignificance. Every star we have observed so far, every planet we might discover, every possible alien civilization that could exist within our galactic boundaries accounts for less than 1% of the matter in the observable universe. Along with its countless worlds, our galaxy represents a single grain of sand on an infinite beach.
On any autumn night, look toward the constellation Andromeda. This faint patch of light appears ordinary among the surrounding stars. Ancient astronomers cataloged it as a nebula. Modern telescopes reveal a truth that should be equally terrifying and inspiring. You are looking at another galaxy containing more than 1 trillion stars. The Andromeda Galaxy stretches 220,000 light-years across, which makes it more than twice the diameter of our Milky Way. This galactic giant contains enough stellar furnaces to dwarf our local star count by a factor of 3 or 4. If our galaxy were New York City, Andromeda would represent the entire east coast of the United States. However, confirmed measurements reveal something even more striking. Andromeda is racing toward us at a speed of 250,000 miles per hour. This cosmic collision course will result in the most magnificent event our solar system will ever witness. Computer simulations show that within 4.5 billion years, these two galactic titans will merge in a gravitational dance lasting several billion years. The collision will reshape both spiral structures into a single elliptical galaxy, already referred to by astronomers as Milkomeda. During this merger, our solar system will likely remain intact. The vast distances between individual stars mean that even during galactic interactions, stellar collisions are extremely unlikely. Instead, gravitational forces will hurl our Sun and its planets into new orbits around the merged galactic center. Yet what truly bends the mind about Andromeda is not its size or its approaching collision, but what it represents about cosmic distances. The light you see from Andromeda tonight began its journey 2.5 million years ago when these photons started traveling toward Earth. Early human ancestors were just learning to use stone tools. The galaxy you are observing existed before modern humans evolved. Even more disturbing is what Andromeda reveals about cosmic scales. Despite being our nearest large galactic neighbor, it is so distant that light requires millions of years to bridge the void. This distance represents the smallest meaningful step beyond our local galactic environment. Our galaxy does not drift alone through cosmic space. The Milky Way belongs to a gravitational family known as the Local Group, which contains more than 50 individual galaxies locked in an endless cosmic dance. This galactic neighborhood spans roughly 10 million light-years and possesses enough combined mass to bend space and time across vast distances. Confirmed observations reveal that most of the galaxies in our local group are dwarf systems, each containing only a few billion stars. These cosmic runts orbit around the two dominant spiral galaxies, our Milky Way and the approaching Andromeda. The most prominent dwarf companions are the large and small Magellanic Clouds, visible to observers with the naked eye in the southern hemisphere. Scientists have discovered that our galaxy is actively cannibalizing its smaller neighbors. Tidal forces created by the Milky Way's immense gravitational field strip stars and gas from the Magellanic Clouds, feeding the material into our galactic disk. This cosmic feeding process has continued for billions of years, and our galaxy grows by consuming nearby dwarf systems. The local group itself moves through space as a coherent unit. Our entire galactic neighborhood travels toward the Virgo cluster at roughly 400 miles per second. This motion carries our local collection of galaxies across distances that dwarf individual galactic scales. Galaxy clusters represent the largest gravitationally bound structures in the universe. These cosmic cities contain thousands of individual galaxies held together by forces so powerful that they warp space and time across millions of light years. The nearest large cluster, called Virgo, contains more than 1,300 galaxies and is 54 million light-years away from our local group. Confirmed measurements reveal that galaxy clusters should not exist according to the visible matter we observe. The combined gravitational pull of all the stars and gas in cluster galaxies cannot explain the immense forces required to hold these structures together. Galaxies within clusters move at speeds approaching 3 million miles per hour. Such speeds should have scattered cluster members into cosmic space billions of years ago. The solution to this puzzle required discovering that most cluster mass remains completely invisible. Dark matter outweighs visible stars and gas throughout galaxy clusters by ratios of 10 to 1. This mysterious matter reveals itself only through its gravitational effects on light and matter, creating a cosmic scaffold that we can map but cannot directly observe. The most spectacular example of dark matter evidence comes from the Bullet Cluster, where two galaxy clusters collide at speeds exceeding 10 million miles per hour. During this cosmic collision, visible gas clouds interacted and slowed down, but the dark matter components passed through each other unchanged. Gravitational lensing maps show that dark matter and visible matter are separated by millions of light-years. Superclusters represent the largest confirmed gravitational structures in the universe. These cosmic formations extend across distances so vast that light requires hundreds of millions of years to cross them. Our local group belongs to the Laniakea supercluster, a gravitational collection spanning 500 million light-years and containing more than 100,000 galaxies. The discovery of superclusters revolutionized our understanding of cosmic organization. Rather than being randomly scattered through space, galaxies arrange themselves in vast networks connected by filaments of dark matter and gas. These cosmic highways channel matter across distances that dwarf individual galaxy clusters. By tracking the strange motions of thousands of galaxies, scientists mapped our local supercluster. By measuring these gravitational flows, astronomers revealed that the Milky Way and millions of neighboring galaxies are all flowing toward a massive gravitational attractor. This attractor, called the Great Attractor, contains the combined mass of tens of thousands of galaxies concentrated in a region hidden by dust clouds in our galactic plane. Step far enough back from the universe and a striking pattern emerges.
Galaxies do not scatter randomly through space. They arrange themselves in a vast three-dimensional network resembling soap bubbles floating in the cosmic darkness. This structure, called the cosmic web, represents the largest scale organization of matter in our universe. Computer simulations confirm that this web-like architecture naturally formed through gravitational processes that began shortly after the Big Bang. Dark matter began to clump when the universe was only a few 100,000 years old, creating gravitational seeds that eventually became the cosmic scaffold we observe today. The cosmic web consists of 4 distinct components working together across billions of light years. Dense nodes mark the intersections where galaxy clusters form. Filaments stretch between nodes like cosmic highways, channeling matter across vast distances. Walls form sheet-like structures where filaments intersect. Between these structures lie cosmic voids containing almost nothing. By observing millions of galaxies and measuring their three-dimensional positions in space, scientists mapped this cosmic architecture. The resulting surveys reveal that galaxies trace the edges of enormous bubbles, while void regions occupy the bubble interiors. This foam-like structure extends across the observable universe with remarkable consistency.
The scale of the cosmic web challenges human intuition. Individual filaments stretch across hundreds of millions of light years, while remaining only 20 million light years wide. These cosmic threads appear impossibly thin when viewed on universal scales, yet they contain enough matter to feed billions of galaxies. Imagine a sphere of space 300 million light years wide, containing almost nothing. In this cosmic desert, no galaxy shines, no star illuminates its darkness. This empty region, called a cosmic void, represents one of the most mysterious regions of our universe. Discovered in 1977, the Bootes Void contains fewer than 60 known galaxies, while spanning a diameter of 330 million light years. Confirmed observations reveal that cosmic voids occupy roughly 80% of the universal volume. These enormous empty regions separate the cosmic web filaments where galaxies cluster together. Despite their vast size, voids contain less than 15% of the average matter density found elsewhere in the universe. The largest solid structures in the observable universe extend across distances so vast that they challenge the fundamental limits of what cosmic physics should allow. These enormous galaxy walls and sheets span billions of light years while maintaining a thickness of just 20 million light years.
The Coma Wall, the first galactic wall discovered by astronomers, stretches across 500 million light years while measuring only 16 million light years thick. The Sloan Great Wall spans 1.3 billion light years in width, making it one of the largest known structures in the universe. Even more striking is the Hercules Corona Borealis Great Wall, discovered through mapping gamma-ray bursts from distant galaxies. This structure is measured to be 10 billion light-years wide. Point the most powerful telescope ever built at any small patch of the seemingly empty sky. Keep the camera open for days, collecting every photon arriving from that cosmic direction. The resulting image will reveal something that should fundamentally change the way you think about existence. That tiny region, no larger than a grain of sand held at arm's length, contains thousands of galaxies. Created by combining 800 separate images with a total exposure time of 11 days, the Hubble Ultra Deep Field revealed more than 10,000 galaxies in a patch of sky covering just 1/13,000,000th of the celestial sphere.
Each galaxy in this cosmic census contains billions of stars, most of which likely host planetary systems where life could exist. The latest estimates based on data from the Hubble and James Webb Space Telescopes suggest that the cosmic volume we can currently detect is filled with 2 trillion galaxies. 2 trillion represents a number that overwhelms human comprehension. If you could observe one galaxy every second without stopping, it would take you 63,000 years to see them all. Each of these galactic islands contains its own stellar populations. Conservative estimates suggest that the average galaxy contains 100 billion stars. Multiplying the number of galaxies by their stellar populations yields a cosmic census producing individual stars exceeding 10 to the 24th power. This number exceeds the number of grains of sand on every beach on Earth. Walk along any ocean shoreline and take a handful of sand. Count the individual grains between your fingers. A typical handful contains roughly 10,000 small pieces of rock and shell. Now expand your count to include every beach on Earth. Scientists estimate that Earth's beaches contain approximately 7 quintillion grains of sand. This astronomical number of Earth's sand grains pales in comparison to cosmic stellar populations. Confirmed observations reveal that the observable universe contains more stars than grains of sand on Earth. Every time you take a handful of beach sand, remember that for each grain between your fingers, cosmic space contains thousands of stars.
However, this comparison becomes even more astonishing when we consider planetary populations. Modern exoplanet surveys suggest that most stars host at least one planet, often within many systems containing multiple worlds. If conservative estimates are correct, the observable universe contains more planets than grains of sand on Earth multiplied by the total number of atoms on Earth. The universe you can see tonight has limits, not physical walls marking the end of space, but fundamental boundaries imposed by the speed of light and the age of cosmic time. Confirmed measurements reveal that this observable sphere measures 93 billion light-years in diameter. This distance represents the maximum extent of space from which light has had time to reach Earth since the universe began. The calculation behind this cosmic boundary requires understanding both light travel time and cosmic expansion. Light from the most distant observable objects began its journey 13.8 billion years ago, when the universe was only 380,000 years old. However, during the travel time, cosmic expansion stretched the space between source and destination. Objects that emitted light 13.8 billion years ago are now 46.5 billion light-years away.
The edge of the observable universe coincides with the cosmic microwave background radiation. Radiation that emerged when atoms first formed and space became transparent to light. This radiation provides a baby picture taken when the universe was less than 1% of its current age. Space itself moves faster than light. This statement appears to violate Einstein's cosmic speed limit, yet confirmed observations proved that the fabric of spacetime expands at rates that dwarf the speed of photons racing through the cosmic void. Einstein's relativity forbids matter and energy from traveling through space faster than light. However, space itself is not subject to such a restriction. The universe can stretch its own fabric at any rate without violating physical laws. Galaxies at the edge of our observable universe are currently receding from us at speeds approaching 3 times the speed of light. Yet those same galaxies are not actually moving through space at relativistic speeds. Instead, expanding space carries distant galaxies like passengers on a cosmic escalator. The discovery of accelerating cosmic expansion won the 2011 Nobel Prize in Physics. Observations of distant supernovae revealed that expansion rates increase over time, rather than slow as astronomers expected. Dark energy, which makes up 68% of the universe's contents, drives this accelerating expansion against gravitational forces.
The Hubble volume represents the maximum spatial sphere that Earth could theoretically influence through any physical process. This cosmic region measures approximately a 14 billion light-year radius. Within the Hubble sphere, space expands at exactly the speed of light relative to Earth's position. Beyond the Hubble distance, space expands faster than light, rendering communication impossible regardless of signal strength or transmission method. However, the Hubble sphere continuously shrinks as dark energy acceleration increases cosmic expansion rates. Currently, galaxies within Earth's sphere of influence cross beyond the Hubble distance at an accelerating rate. Every day, cosmic regions equivalent to millions of Earth-sized volumes permanently pass beyond our ability to influence through any physical mechanism. Beyond our cosmic horizon, an infinite number of parallel universes may lie, containing different versions of reality, where alternative histories unfold according to quantum probabilities. This multiverse hypothesis arises naturally from cosmic inflation theory and quantum mechanics, suggesting that our observable universe represents only a single bubble within an infinite cosmic structure.
Eternal inflation models propose that new space is continuously created through quantum fluctuations in the cosmic vacuum. These fluctuations create bubble universes that expand into separate cosmic regions, each potentially developing different physical laws and containing unique arrangements of matter and energy. If eternal inflation is correct, then every possible quantum outcome occurs somewhere within an infinite multiverse structure. In an infinite multiverse, every possible arrangement of atoms must occur somewhere, including perfect copies of our observable universe repeated across cosmic space. Identical copies of Earth containing exact duplicates of every human would exist in numbers approaching infinity. Theoretical physics suggests that our entire observable universe, containing 2 trillion galaxies across 93 billion light-years, could be smaller than a subatomic particle within a much larger cosmic structure. This mind-shattering possibility arises from models that propose infinite hierarchies of organization, extending far beyond anything humans can observe or imagine. An atom measures approximately 1/110 of a meter in width. If our observable universe, spanning 93 billion light-years, were compressed to atomic scale, the larger cosmos containing it would span inconceivable distances. The ratio between our universe and this hypothetical larger structure exceeds the ratio between an atom and our observable cosmic volume.
If there are infinite hierarchies of organization, then the larger structure that contains our universe itself could be smaller than an atom within an even larger cosmos. This recursive scaling could continue infinitely, making our observable universe infinitely small compared to ultimate reality. You are reading these words on a planet orbiting a star in a galaxy among 2 trillion cosmic neighbors spread across an observable universe that could be smaller than an atom in ultimate reality. This perspective places human existence into a context so vast that it challenges every assumption about importance, purpose, and cosmic significance. Earth measures roughly 25,000 miles in circumference, a small rock spinning through space at 67,000 miles per hour around a nuclear furnace that consumes 4 million tons of matter every second. Our Sun ranks as a perfectly average star among 400 billion stellar furnaces that fill our galactic neighborhood.
The Milky Way galaxy spans 100,000 light-years, while containing enough stellar material to power quadrillions of civilizations. Yet our entire galactic home represents only a single grain of sand on an infinite cosmic beach containing more galaxies than grains of sand on every beach on Earth. Each of these 2 trillion galaxies contains billions of stars, most hosting planetary systems where conditions could support life. Conservative estimates suggest that hundreds of billions of Earth-like worlds exist within our observable cosmic volume. Some of these planets likely developed civilizations millions of years before human society emerged. Yet the observable universe itself may represent less than 1% of total cosmic reality. Beyond our cosmic horizon lies a potentially infinite universe extending in all directions, containing hidden infinite numbers of galaxies, stars, planets, and possible civilizations. This cosmic perspective simultaneously renders human existence infinitely small and profoundly meaningful. We represent temporary patterns of organized matter that have acquired the remarkable ability to contemplate cosmic scales far beyond our evolutionary origins. Humanity evolved from simple chemical processes on a small planet, yet we have discovered cosmic structures spanning billions of light years.
The same cosmic processes that created galaxies, stars, and planets also created the complex chemistry that led to biological evolution and human consciousness. We are literally made from stellar material, forged in nuclear furnaces and scattered into space by stellar explosions. Every atom in your body, except hydrogen, was created inside a star that lived and died before our solar system formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all came from stellar nucleosynthesis that occurred billions of years ago in cosmic neighborhoods far from Earth. This material connection binds humanity to cosmic evolution across space and time. We represent the universe becoming aware of itself, matter gaining consciousness, and developing the ability to examine its own cosmic origins. Despite occupying a small corner of an infinite cosmos, humans have discovered fundamental truths about reality that apply on cosmic scales. We have glimpsed the true scale of existence. The universe is not only stranger than we imagine, it is stranger than we can imagine, and we are here to witness it. Do not forget to subscribe and like for more videos. Good night.